We've just finished the first quiz, and you turned in homework 4 today. I sent out a little video clip last night after I had a good question during my office hours about how to solve the equations. And in that video clip I sent you last night, it was referring to Wolfram Alpha. I'm just curious, how many of you ended up using Wolfram Alpha on the assignment? A couple people? Night owls probably, right? Okay, because I didn't send that email out to about 9 o'clock. So I'll send it earlier next semester. It's just something I thought of last night. Probably a lot of you already had the assignment finished when I sent you that.
Are you going to grade it with kind of like a kind heart?
I grade everything with a kind heart. I'm a huge softie. Yeah.
You don't grade it though, do you?
I'll grade these quizzes. Oh, the homework, right. Good question. Yeah, because I do have a grader now. I'll make sure he has a kind heart as well. It's a sword and a stone situation. You got to be a real sweetheart to grade hydraulics. That's the chief criteria. All right. All right, so your next homework assignment, number 5, is related to Hardy-Cross method. I think you'll enjoy that one more than you enjoyed this one, because this one was a lot of logic, a lot of plug and chug, so it's labor intensive, and I know it. But for homework 5, that'll be due next Wednesday, so you'll have a week for that. I haven't posted it yet on Blackboard, but I'll do that this afternoon. What we're going to do today is finish the example number 2 that we were working in on Monday, and we didn't get through calculating the pressure at each junction. So we'll do that, and then we'll spend some additional time working on Hazen-Williams equation problems. So, question?
Wednesday the 15th, right?
Oh, is it the 15th?
I think I was
Let's
going to
see.
double check.
You're right. Yep, 15th. Ben's got a sharp eye, and he got you an extra day on the assignment. Are there other questions? Okay. So where we were last time on this example, we had, in the first iteration, used the fully turbulent flow assumption to calculate our initial F values. We calculated R's. We put in our initial flow guesses based on the initial flow balance. In the second loop, remember that the key thing that we did there that was a little bit different was related to the common pipe. These ones that are in bold are the pipes that are going to exist both in loop 1 and loop 2. So instead of using my original flow rate, I used equals negative of the corrected flow rate from the previous loop. So the minus sign just to correct for the change in perspective that arises when you're looking at clockwise from loop 1 perspective versus clockwise from loop 2 perspective. So that's a required step to have the negative of the previous step flow rate. So that was our first iteration. In the second iteration, we switched over from the fully turbulent flow assumption to calculating the full version of the Jane equation for our F values, because now we've got flow rates, we've got velocities, therefore we know Reynolds numbers, and so these F values are going to be more accurate than the first initial guesses that we used in the iteration 1. The other difference is that we're not starting off with my guess flow balances, but we're using whatever the most recent guess is. And so for pipe A, B, and BC, for example, it's just the guess from the previous iteration. But then these common pipes, which are in bold, we are using whatever the latest updated flow rate is for that particular pipe. So doing that, after 4 iterations, things had converged pretty nicely. We still have a little bit of a flow rate adjustment for pipe BC simply because it's such a low flow rate pipe. But in this column adjacent to our 4th iteration, I calculated the head loss through each of the pipes. So the H sub F, the head loss due to pipe friction, we're applying the formula that head loss is R times Q to the n power. So our last R value is, let's see, it is in column I. So here's our final R values. So these head losses are R times Q to the power of n, which is 2. So it just says through pipe AB we lose 3.49 meters of head. Through pipe BC, it's not actually 0. It's just that the flow rate is really low. It's a small number. If we show all the digits, we can see it. So this is the head loss through each of the pipes. And so here's the final flow rates. And regardless of what your starting flow guesses were, you should end up with something relatively close. After 4 iterations, I'd expect that regardless of what your starting values were, you should be within 1 or 2%. Now, it'll never converge if you don't have continuity at each junction to begin with. It'll also never converge if you have any kind of typo in the spreadsheet. So that's tricky. But there was what I'm going to call a control point at junction A, where the pressure was known and defined as 600 kilopascals. And so we can determine the head at that junction by, it's the 600 kilopascals divided by 9.81. So starting off, there's 61.16 meters of energy at A. And since the water is flowing from A towards B, then the energy is decreasing. So what I said is, you can see in the margin here, the formula is that the head at B is however much head there was at A minus the loss through the pipe. So I'm going to say it's the head at A equals the head at A minus the loss through AB. Okay, so now I know the head at B, and then therefore the pressure at B is going to be the head times 9.81, because that's how many kilonewtons per cubic meter there are for water. So that tells me the pressure was 600 kilopascals at A. Now the pressure at B is 565 kilopascals because of the losses. And we can go through this process of looking at the next junction in row. So like junction C will have more head than junction B does because of the flow direction. Water wouldn't be going from C towards B unless location B had less energy. So C has to be higher. So the little formula that I've got here, it's going to be the head at B plus the losses through that pipe. So it is equal to the head at B plus the losses through pipe BC. There's not much loss. So it's going to be pretty close to the same pressure at location C, very subtle, and that's why the flow rate is so small. There's not much of a flow rate if the pressures are almost the same. I guess if I extend the digits here, you can begin to see there is a subtle difference in the pressure between those 2 points. Okay, junction D is here. It's going to have more pressure than junction C did. So it is the head at C plus the losses through pipe CD. And here's that loss through the pipe. And then again, the pressure is just the head at that location multiplied by gamma. All right. The head at E is going to be less energy than at C. So it is the energy at C now minus the losses because of the flow direction. So I need to have the losses through pipe CE. I'll click here for that. And I can just drag the cell down to find the pressure at that location. And finally here at F, it will have more head at F than we could use it in terms of D, A, or E. We could use any of those to find out what's the head at F. So here, the little formula that I have in the side here, it says it's the, I can't see because this is in the way. Let me see if I can dismiss that. No? It says the head at F, oh, it can't be the head at itself. I'll say it is the head at E plus the losses through the pipe. So it is the head at E plus the losses through EF. Okay, so now we know the pressure at each of the junctions aside from the control point where we already knew the pressure. And if we put that into, and we will, put this system into water gems when you're first learning how to use that, because we know that this is right. We set up the equations ourselves. We calculated the pressure ourselves. Like going back to first principles, we know that this is the correct flow rates for this system. So we'll kind of validate that this black box software, water gems, is doing what we expect when we create the same network in water gems in a couple of weeks. But until then, are there any questions about this example that I can answer now? If you still don't have a functioning example spreadsheet, I'd love to have you stop by my office, and I'll do whatever I can to help you find your mistakes and troubleshoot, because it's really easy. The common mistakes that I see most of the time would be forgetting the minus sign in this formula. Just, I don't know, it doesn't jump out at you, but there's a minus sign in the correction. So that's one of the favorite mistakes. Another favorite mistake would be forgetting to switch over to the full version of the Jane equation. And then forgetting to do the minus sign when you are working with these common pipes. All right. So unless there's any questions, we'll move on from this. Ben?
It's more of a theoretical question.
Mhm.
Like, why would you design like a pipe network that splits in so many different ways rather than just having a singular flow?
Yeah. I think probably the justification for a network like this would be redundancy, where if one of the pipes has to be closed off for cleaning or because of damage, that all of the junctions still get water.
Okay.
So he's right that we could have had water going from A to B to C. Like we could have all of these served and eliminate CE, and you could still get all water to each of the junctions with CE eliminated and BC. You'd still get water to all the places you want, and you could eliminate 2 pipes. But then you'd have dead ends where if the pipe is, if one of the junctions isn't drawing water, the water can become stagnant. And also there's the risk that if one of the pipes breaks, that then they lose pressure at the junction. So it's just redundancy. Are there other questions? In the project, you're going to have to make that same decision about whether to have redundancy or whether to save money by having junctions that are served only by a single pipe. You'll have to look at how much extra it would cost to provide that redundancy. So it's an interesting and appropriate question. All right, so we finished the example. Now we're going to do some Hazen-Williams equation problems, just so that you don't forget or lose sight of that very useful method, because there are likely to be Hazen-Williams equation problems on the FE. So I have this handout for you. All right, so I'd love it for you to work with your classmates on both of these problems. There's one on the front side of the paper, one on the back. Just getting some extra practice and thinking about the kind of situations where if you don't have to calculate some updated F value, the way that you can use the constant coefficient C value that you'd apply in the Hazen-Williams equation to find the, in the case of the first problem, sorry about that, the downstream flow, the flow rate in the pipe, and then in the second one, we're working in traditional units, which is always a little sticky, but trying to find out the pressure at that location downstream. If you want to check your work for the first problem, it's here, the solution is up on the screen. So the head loss, slope of the energy grade line. I didn't calculate the velocity separately. I went straight to the flow rate by multiplying it by the area here. Should have 124 liters per second. Okay, so on the second problem, keep in mind that since we have BG units, British gravitational units, we have to convert from inches to feet. And then, let's see, what's the other tricky part about it? I guess maybe that's the only tricky part. Yeah, PSI. Good. So here's the solution to that second one. Well, let me zoom out a little bit. There it is. I can't have it everything. Anybody have any questions on the second example, why things are the way they are? Of course, in a pipe where the diameter is the same at the upstream and the downstream location, the velocities are the same. So I've eliminated the velocities out of the energy equation when I was rearranging it to solve for P2. So in this one, part of the reason why the pressure changed is because it's downstream, but also partly the pressure changed because of the elevation difference. So that's why we have to use the full version of the energy equation here to account for both of those independent factors. It's the pressure downstream is going to be the original pressure, the net difference in elevation effect, and then the head loss effect. So we're going to keep track of all of those terms, and you can see here that I've tabulated what that is in terms of head and the relative changes by each parameter. So we should get that the downstream pressure is 62.9 psi. All right, we're out of time. It's 1:50. I'll see you in class on Friday, and I'm going to post the Hardy Cross assignment on Blackboard if you want to get started on that. Have a good day.